Hello, class. Okay, so we're going to study gases today, and in particular, we're going to look at what we call an ideal gas. And so based on the title, it says ideal gas, macroscopic. We're kind of following this historical way the subject was developed. And the atomic theory of matter, like the very existence of atoms, was kind of disputed until 1905. The idea was not fully accepted, and a lot of our work on gases predates that. They didn't even know about atoms when they developed a lot of the stuff we're talking about here. So we're going to look at it from that approach, where we're going to kind of base. There are certain experiments that were done that kind of led to what we call the ideal gas law. And then later on, we're going to look at a microscopic approach, where we're going to look at a gas as a collection of atoms and molecules and kind of derive the same result. So the macroscopic approach. Oh yeah, and we're studying gases, but in particular, what we call an ideal gas. So we have a gas that's in some container, and the in a macroscopic approach. I guess we have to kind of introduce the idea of atoms now, even though we're doing a macroscopic approach. But we have a container filled with atoms and molecules, and what an ideal gas is, it's basically when the spacing between the atoms is much greater than the size of the atoms themselves, which is very frequently going to be the case. And if you cram enough gas in here, they don't have the same freedom of movement. So we assume these molecules move around, and they don't really exert any significant forces on each other unless they collide. And then when they collide, the collision is elastic. Similarly, when they collide with the walls of the container, those are elastic collisions. Okay, so what we're talking about, we're going to derive a law, or based on experiments, that applies to ideal gases. So what we're talking about does not hold true in general. Like if you have a very high pressure system or high density gas, this may not hold up. Okay, so we're taking this macroscopic approach, and we can describe the gas with several quantities. We can talk about pressure of the gas. So pressure, as we know, is force over area. So if you look at a certain area of the container, we can measure the force. Gases push outwards on the walls of their container. And if we measure the force on that section of the wall, divide that by the area of that section we're considering, that would be the pressure of the gas. Volume. So just, the volume of the gas, typically it'll be contained in some container, although maybe not always an actual physical container. Like our atmosphere is confined to a certain volume, but that's held up by gravity. Temperature, I'm going to write absolute temperature. And also the amount of the gas. So these are large-scale things that we can measure about this gas without really knowing what it is, what the gas is, like what's going on below the surface, which we now know, atoms and molecules. But these are things that are more accessible that we can measure. And I want to start by talking about the amount of gas. there's two ways we can describe the amount of a gas. One is the number of particles. And the other is the number of moles. So, what are moles? Basically, it's a way of measuring things where 1 mole of a substance contains a certain number of particles, or a certain number of objects. And that number is called Avogadro's number. And numerically, Avogadro's number is 6.02 times 10 to the 23rd power per mole. And so basically, like 1 mole of, say, carbon atoms has 6.02 times 10 to the 23rd power carbon atoms. 1 mole of, say, hydrogen molecules has 6.02 times 10 to the 23rd molecules. So it'd have twice that number of atoms because each molecule has, for hydrogen, each molecule would have 2 atoms. And, this generally applies. You could say, 1 mole of marbles would have this many marbles. That would be an enormous number. But, n is the number of individual particles. Lowercase n is the number of moles. And either one can be used to describe the amount of gas present. And if you know one, you know the other. You can convert by Avogadro's number. Now, there were a series of experiments done on gases that found relations between, so again, we have 4 kind of variables here: pressure, volume, absolute temperature. So remember, that's based on like a Kelvin scale, and the amount. And there are several of these. Let me just erase these and replace them with the symbols. We'll just stick with moles for now. So we have pressure, volume, temperature, and amount in moles. Okay, so there were several experiments. There's 4 variables involved. So what these experiments did is they held several of the variables constant and then just, varied one at a time and saw the effect on another variable. So the first one, we have something called Boyle's law. So Boyle's law, let's get we fix the temperature and the number of particles. And what Boyle found is that the pressure of the gas is inversely proportional to the volume. So say you have a container, like a cylinder with a movable piston, and you have to do this at a fixed temperature. Normally, like if you were to compress the gas, that would heat it up. So you have to make sure that you're doing this without changing the temperature. But then if you do that, if you, say, lower the volume, that would increase the pressure. If you reduce the volume, if you go down to a factor of 1/2, 1 over 1/2 is 2. You double the pressure. So that's Boyle's law. And I never keep these names straight, but then there is Charles' law. Where Charles would fix the pressure and the number of, the first three, we're going to just have a particular gas where we keep the amount of gas fixed. You don't let any escape or enter the system. So if we fix the pressure, then and the number, we're looking at a relation between volume and temperature. And what Charles found is that the volume is proportional to the temperature. So again, you fixed the pressure. So let's say you have a gas at a certain temperature, and it'll occupy a certain volume. So what if you double the temperature? And again, just to be clear, we're talking about absolute temperature. If your gas is at, say, 20 degrees Celsius, doubling the temperature does not mean 40 degrees Celsius. You'd have to convert to Kelvin, so it'd be about 293 Kelvin, and then you double that, so it'd be almost 600 Kelvin. So if you double 20 degrees Celsius, then that would be the temperature. If you double the temperature, it'd be like 350 or 340 or something Celsius. But anyways, if you double the temperature of the gas while keeping the pressure constant, then the volume will double. And then there's Gay-Lussac. Or L-U-S-A-C. And what he did is he would fix the volume and the number of particles. Again, keeping the same gas, same number of particles. So if you fix the volume and the number, you're looking at a relation between pressure and temperature. And then he found there's a direct proportion between them. So if you double the temperature, you double the pressure for a fixed volume. And then finally, we're going to look at the number of particles. How that, what if you change the gas? So you have a gas. What if you insert more gas? And that was Avogadro. See if I can cram that in here. So Avogadro did this experiment where what he did is he fixed the temperature and the pressure. So, temperature and pressure. So then we can just isolate these two variables, the volume and the number of particles. And he found that the volume proportional to the number of particles. So if you have, say 1 mole of gas at a certain temperature and pressure, then that will occupy a certain volume. If you have 2 moles of gas, that would take twice the volume at the same temperature and pressure. So again, gases, they're complicated. They have, all these different variables that are related to each other. So each of these experiments, you fix 2 of the variables and see how the others are related to each other. Try to find a relation between them. And so we have all these results, and we can kind of put this all together into a single equation called the ideal gas law. Actually, I'm not going to write it there yet. So what we have is pressure times volume is proportional to the amount of gas times the temperature. We can kind of check and see, that all of these laws are contained in this one equation. So let's look at Boyle's law. If we fix the temperature and the number of particles, temperature and number of particles, basically what we get is pressure times the volume would be equal to a constant. The right side is constant. And so, pressure is inversely proportional to the volume. You multiply the two and they're constant, then that's an inverse relation. Like pressure times volume is proportional to 1 or equal to a constant. let's look at Charles' law. If we fix pressure and number of particles, so these are constants, we get the volume is proportional to the temperature. Basically, these proportional relations, we don't care about constants in those, so we can just kind of delete these two. If they're constant, they don't matter. Like we could divide by pressure. We get volume is proportional to N over P times T, but N over P is a constant, so volume is proportional to some constant times a temperature. Again, a constant's irrelevant. Now for this Guy-Lussac law, we fix the volume and the number of particles. So again, just ignore those two variables. Pressure is proportional to temperature. And finally, if we fix temperature and pressure, we get volume is proportional to the number of particles. And so this is the ideal gas law. It's like a proportional relation. Now what we'd like to do is turn this into an actual equation. And to turn a proportional relation into an equation, all we do is introduce a constant. However, we actually have two constants here. I'm going to write down one form of the ideal gas law. So the constant we're going to throw in there is this capital letter R, which is a universal gas constant. And this is 8.3 joules per mole Kelvin. So that is, it's got a universal gas constant. Now, said we're going to have kind of two ways of doing this, because for any particular problem, like remember we can describe the amount of a substance using either moles or the number of particles. And so we could just stop here and say, that's it. If you have the number of particles, we know it's related by Avogadro's number. So if I give you a problem with a certain number of particles, you could just convert to moles and then use this equation. But because the two different ways of describing the amount, they both occur relatively frequently. And so instead, we're going to introduce another constant. I'll write it KB. So capital N, that's the number of particles, times this new constant, which is called Boltzmann's constant. And then times absolute temperature. And Boltzmann's constant is about 1.38 times 10 to the minus 23rd joule per Kelvin. And so again, it's not really necessary to have both of these, but it is convenient. And you have an equation sheet that has this. So you just use whichever version of the ideal gas law. If you want to know the number of moles, or if you're given a number of moles, use R. Otherwise, use Boltzmann's constant. We're going to come across Boltzmann later. He did a lot of work on what we call the kinetic theory of gases. So like we're looking at a macroscopic approach right now, but what Boltzmann did is he considered a gas to be a collection of molecules and did a lot of very, very impressive work, deriving the ideal gas law, things like that. Actually, I think that was done before him, but he did a lot of work with gases based on what's called kinetic theory, where you consider these molecules moving around and bouncing off the walls and things like that. And according to the story that I read, this was before atoms were fully accepted, so his work was looked at very skeptically, and I guess he got depressed and killed himself. They say that might have been the reason why. But shortly afterwards, atoms were fully accepted, and his work was seen as very, very important. Okay, so this is the ideal gas law. And again, typically you can assume that a gas is ideal because normally the spacing between the atoms and molecules is very large compared to the size of the molecules themselves. Molecules are very small. And so they have plenty of room to move around without interfering with each other. Now, under extreme conditions, this law would not hold up anymore. But as far as we're concerned, unless you have a reason to believe otherwise, you can use the ideal gas law. Okay, so that's the macroscopic approach. We'll come back and look at a microscopic approach later. But for now, that'll be it.